Hello and welcome to this video in which I show you how you can fit a random intercept factor model in the Mplus software. My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. On Tuesdays I present an analysis in the Mplus software, and on Thursdays I talk about more general issues in statistical analysis, including structural equation modeling, factor analysis, latent class modeling, and multi-level analysis. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional resources, including a link to my free weekly statistics newsletter and to workshops that I offer through QuantFish. In this video, I want to show you how you can fit a random intercept factor model in the Mplus software. What might such a model be useful for? One example is that when we have longitudinal data, that we want to sometimes test the baseline hypothesis that there was no change across time before we fit more complex models, such as, for example, latent growth curve models that imply that there were changes across time in the score. So for example, here you can see a path diagram of a random intercept factor model for 4 observed variables, y1, y2, y3, and y4 are the observed variables here. Intercept is the factor, the random intercept factor, and here in this case it could be that y1, y2, y3, and y4 represent repeated measurements of, for example, intelligence scores over time from the same people. So this would be measures, so say, of the same IQ test on 4 different time points. And now we could test with a random intercept factor model whether intelligence scores, intelligence true scores, were perfectly stable across time by fitting a random intercept factor model. A random intercept factor model is a special case of a single factor confirmatory factor analysis model where, as the name says, there's just a single random intercept factor. All factor loadings are fixed to be equal, so that you can't see that here in the Mplus path diagram, but all these loadings, as we will see later in the syntax file, are constrained, are fixed to 1, so that the intercept factor has the exact same impact on all these observed variables. And in addition, there's also no additive constant in this special type of factor model. All the intercepts or additive constants of the observed variables are fixed to 0, so that the mean structure comes only from the random intercept factor. So all this implies that all means are equal and that the true scores don't change across time, because the impact of the random intercept factor on each of the observed variables is the exact same. So it's a very simplistic measurement model that says that yt, the variable, observed variable y at time t, is a function of just the intercept random factor plus measurement error epsilon, which is indicated here by these arrows on the right hand side of the path diagram. Those would be error terms. And so there can be variability in the observed scores across time for each individual, but this variability can only be due to measurement error. The true scores don't change. Another application of this random intercept factor model with equal loadings and 0 additive constant intercepts is in classical test theory. There's a model in classical test theory that's called the model of tau equivalence. With tau equivalence, we have the exact same structure for cross-sectional data. So if we have tau equivalent measurements of the same construct, for example, if y1, y2, y3, and y4 were different IQ tests measured at the same time point, then we could test the hypothesis that those 4 different IQ measures are tau equivalent, meaning that they share the exact same true score variable. And then that model could also be fit with equal loadings, 0 additive constants, and freely estimated error variance parameters. So that would be another application of a random intercept factor model, which then would be called the model of tau equivalence. And I have another video on this channel here where I talk about the model of tau equivalence and how it's fit in the Mplus software as well. You can also check out my playlist on classical test theory analysis in Mplus, where I discuss different models. Also, I have a separate video in which I talk about the random intercept model conceptually in more detail on this channel. You can also look at that if you want to know more about the theoretical background of the random intercept model. Now let's take a look at how this model is actually specified in the Mplus software. And so I already ran this model in Mplus. So here you can see the syntax in the first portion of my output. And so in this case, it's a model that was fit to hypothetical IQ data at 4 measurement occasions. So this would be the longitudinal application of the random intercept factor model, where the scores y1 through y4 represent repeatedly measured scores on the same measure, the same IQ test across time for the same people, and where we want to test the hypothesis that there hasn't been any change, there hasn't been any changes in the true scores on the IQ measure by fitting this random intercept model. So now that we're doing this, you can see here in the model statement in Mplus, I'm specifying a factor called Intercept. That's my random intercept factor using a by statement. The by statement in Mplus stands for measured by. So the intercept factor is measured by my observed variables y1 through y4 with a fixed loading of 1 for each indicator. So every single one of those factor loadings is fixed. None of them is freely estimated. And that's to say part of the issue when we want to interpret this factor as a random intercept factor, we have to make sure that the loadings are all equal. Furthermore, the second subcommand here in the model statement is used to fix the additive constants to 0. So the intercepts that would normally be part of a congeneric measurement model in Mplus, which is the default measurement model in Mplus, would contain additive constants. So automatically Mplus would add intercept, so that your measurement equation would be y equals intercept plus factor loading times factor plus error variable. And so in this special measurement model, the random intercept factor model, we are deleting those additive constants that Mplus would include by default. Otherwise, this model would not be a random intercept factor model. So that's why I'm saying here y1 hyphen y4 at 0. This constrains all the intercepts to 0, so that there's only a random intercept, no fixed intercept. If there were a fixed intercept that would be estimated for the variables, then they could differ in their means. And then that would imply that there could be changes in IQ means across time, which is it's an alternative hypothesis. So say that there are shifts over time in the means that could be tested after testing the random intercept factor model and finding it doesn't fit. That could be the next model to test, where we leave intercepts free so that we can allow for mean differences across time. Now in this model we don't do that. Instead we estimate only a single common mean, the mean of the intercept factor, which is indicated here by the third subcommand in my model statement, where I'm requesting that the intercept factor mean be estimated as a free parameter. And we have to do that because in Mplus by default we would not get a mean for this factor otherwise. Mplus by default, when we have a single group analysis, does not include means for latent factors. And so in this case, we can identify the latent mean because all intercepts are fixed to 0 and also the loadings are fixed to 1. So there's identification is ensured of this common latent mean, and this will be estimated. So this will be the common mean of all variables, implying that there's no shift in the means across time. IQ means are perfectly stable under this random intercept factor model. And again, the specification parallels what we would do in a tau equivalence model for cross-sectional data if y1 through y4 represented different measures of IQ at the same time point. And if we wanted to know whether these measures are strictly tau equivalent, then we would set up the model in exactly this way with equal loadings, intercepts fixed to 0, and the mean of the common true score variable estimated as a free parameter. What are other parameters of this model? The other parameters that are freely estimated here are the variance of the intercept factor. So we are allowing for inter-individual differences in intelligence. However, those cannot change across time, so they're constant, but they're estimated because people can differ. And then also we're allowing the error variances to be estimated for each of the 4 time points. So there will be a separate error variance parameter for each of the 4 time points. This is not shown here in the syntax because Mplus gives you those variance parameters by default. By default, it'll estimate a variance for each latent factor that is in the model, and also a variance parameter for each error term that's automatically included when you specify a factor model. Also included in the syntax is an option for printing sample statistics, so you can take a look at your observed means, covariances, and correlations, and then stdyx to request the standardized parameter estimates, so that you would, for example, be able to look at the standardized factor loadings. And then I included a plot option here as well, so that we can take a look at the observed and model implied growth curves. We'll see that the random intercept factor model implies very restricted growth curves where there's no slope. So say the slope of all growth curves is 0. The growth curves across the 4 time points are perfectly parallel to the x-axis and parallel to each other, so that there are no shifts in the true scores across time. And then we can compare that to the actually observed growth curves in our observed data to see if there's any kind of mismatch, perhaps. So let's take a look at the output for this model. This analysis here was based on 300 cases. There was some missing data, but not very much, as you can see from the covariance coverage here, that the coverage was fairly high for all variances and covariances. And you can see the sample means in this example indicated an increase in average IQ scores from 100 at time 1 to about 105 at time 4. So this might already show us that the model may not fit so well, because this is an indication that there was some shift in IQ scores across time, whereas the random intercept factor model implies that the means were stable across time and that the true scores for all individuals were stable across time, so that this might be at odds with our observed data and this model may not fit very well. You can furthermore see that in the correlation structure that those scores were very highly correlated across time, which is something that we would expect for IQ scores, because we know that there's a high stability of inter-individual differences when we measure IQ scores. So IQ is a trait variable, it's something that is rather stable across time, and that's reflected in these very high correlations of the observed scores across time. So from that perspective, a single factor model might work. However, here it looks like there were some changes across time. So the fact that variables are highly correlated does not mean that there couldn't be changes across time, for example, with regard to the means. And so this seems to be the case here. So let's take a look at the model fit. In the model fit information section, you can see the model estimation terminated normally. So this model converged to a proper solution. There were no improper parameter estimates, but this doesn't mean that the model fit well. So we have to still take a look at model fit statistics, specifically the chi-square test of model fit. And you can see here, it's a very high value of the test statistic that we obtain. The test statistic is 100 and the degrees of freedom are 8. So this would be our chi-square test statistic, and that is a test statistic that is highly significant. The p-value for the test statistic is very low because the test statistic is so much greater than the degrees of freedom. And so this would mean the model is rejected. So the model implied covariance and mean structure does not match up, does not line up with the observed covariance and mean structure. There's some significant discrepancies here. Also, the RMSEA estimate looks bad. This is something that we would like to be small, close to 0, smaller than 0.05 typically, and here it's very large. Also CFI and TLI do not look particularly good, and neither does the SRMR coefficient. That's a summary measure of the model residuals. Let's take a look at the model results. So here you can see in this model all loadings are fixed to 1. By definition, the mean of the intercept factor is estimated, and you can see there's only one mean in the model because the intercepts of the observed variables are all 0. So there's nothing that could add to the mean to allow the variables to shift their means across time. And this could already be a reason why this model doesn't fit well, because it assumes that there's just one common mean that applies to all 4 variables, and that's the 102.878, so about 103. And you can see that that common mean is somewhere in between here of our observed means, which ranged from 100 to 105. And so that's kind of in the middle, our estimate of about 103. And so Mplus tried to give us the best possible mean that minimizes that discrepancy that we see in the observed means, and that may not be good enough. So there may be a significant difference here, definitely between probably an IQ score of 100 and an IQ score of 105. That would be significantly different, whereas the model implies that these means are all the same in the population. And so this might be a reason for this significant chi-square value. So this model only has one common mean, and this may not be good enough. Now we could mitigate this by estimating some of the intercepts. So we could free up the intercepts, for example, for time 2, time 3, and time 4, and then see if that model fits better if we don't fix all the intercepts to 0, but only the first intercept, so that the intercept factor represents the scores at time 1, the true scores at time 1, and then we allow the means to differ across time. This could be an alternative model that we might try out now that this model didn't fit the data well. Another parameter that is estimated is the variance of the intercept factor, and that variance quantifies inter-individual differences in IQ scores, assuming that those don't change over time. So there is variability in the scores that is allowed, but the scores can't change across time. And then finally, we have residual variances estimated that allow us to quantify the degree of unreliability or measurement error in the scores. And you can see that those error variances are freely estimated for each time point, so they can vary across time. They are a bit higher at time 1, which is a typical finding, that there's a higher measurement error component at the first measurement occasion because individuals have to get used to a procedure. They may be more nervous, they make more errors because they don't know how the test works, and then later on they settle in, they know how the procedure works, and then measurement error, often the measurement error component becomes smaller across time. Now we have to be careful overall interpreting these parameters too seriously, because we saw that the model didn't fit the data well. So in this case, we might or we should try a different model, such as one with free intercepts and or one that adds a growth component to the model. For example, we could try a linear growth curve model where, in addition to our random intercept factor model with equal loadings, we also have a slope factor with loadings that are fixed according to linear growth. This is also something that I address on this channel. If you want to take a look at my playlist on latent growth curve models or the separate videos on growth curve models on this channel, that's where I explain how you can fit a model that has a growth factor in addition to the random intercept factor for longitudinal data. Below the parameter estimates, below the unstandardized parameter estimates, we also get the standardized solution because we requested STDYX. And so here you can find the standardized factor loadings which are not equal. And so why are they not equal? They're not equal because the error variances were allowed to differ. And then if that's the case, then the standardized factor loadings will be unequal. So this is not a model that is has strictly parallel measures, but it's one where the error variances and reliabilities can differ across time, and therefore also the standardized loadings are allowed to differ. identification of this solution is achieved by fixing the variance to 1. So in the standardized solution, all variances are fixed to 1, and then that allows us to freely estimate the loadings, and they will differ between indicators unless we also constrain the error variances to be equal across time, which we did not do in this model. We allowed them to vary freely, and then as a result, we get factor loadings, standardized factor loadings that are different between indicators. You can see that they're all pretty strong, and that reflects the strong correlations between the measurements that we saw in our observed correlation matrix, and it means that those are fairly reliable measures of IQ. You can also see this when you scroll down to the R squared. The R squared can be interpreted as a measure of reliability of each test or each measurement occasion, and so you can see that those reliabilities are fairly high. Now again, we have to take these estimates with a grain of salt, and we should interpret them only with caution because the model showed a bad fit. The chi-square was highly significant and large, and so those estimates may be biased. Again, we should look for a better model for these data that fits better, such as, for example, a growth curve model where we also have a slope factor in the model that accounts for differences in change across time and changes at all. So let's take a look at the growth curves that are implied by this model. We can get them here by clicking on plot and then view plots. And let's take a look at the estimated individual values first. So those are the ones that the model implies. So this random intercept factor model with equal loadings and 0 additive intercepts. Let's take a look at those growth curves, and Mplus will show you 10 growth curves at a time by default, starting at index 1. So meaning starting with the first case in the data set, we will get the first 10 curves, and then we can click through the whole data set to look at them. So the model implies, as I told you earlier, that those growth curves are all flat and parallel to one another. So there are no changes in the true scores across time allowed. So all 4 time points have the exact same true score for all people. The people can differ, so there can be between individual differences in the true scores, but no differences across time, which means inter-individual differences and change across time are not allowed, and neither are any changes in the true scores across time. You can click through the entire data set by clicking here on Get Next Sample, and so you can see that's the case for all individuals. All those growth curves are perfectly flat and they will not cross one another. So that's unrealistic, as we will see when we take a look at the observed growth curve. So we'll go back to plot and then view plots, and now we're going to take a look at the observed individual values. So that's the actual data, and again we can look at 10 curves at a time. We can start at index 1 again, so the first individual in the data set. We'll click on OK, and now you can see this is what the actual growth curves look like, and you can see there are some that increase here more than not. So when we click further, you can get a better sense for that. You can see that there are changes across time, and there's also crossing of the line. So some individuals start lower and then end up higher, and so a model that assumes that the underlying error-free curves are perfectly flat is not in line with this data set. So these differences across time are not solely due to measurement error. There are some changes in the true scores, and so this is not reflected well by this random intercept factor model, and therefore this model didn't fit well. I hope you liked this video to learn more about the random intercept factor model and how to fit it in the Mplus software. If you did, then please subscribe to this channel. Don't forget to hit the like button and to check out the description for additional resources. I also offer workshops on longitudinal data analysis, for which you can find the links in the description. So check that out as well, and I'll see you next time.